Mind?
Hi, Bill.
All right.
Hi, Spoonsy.
To start,
Spoonsy, I love you. What?
we need to talk about a number, a new number for all of you. We are skipping ahead a little bit because we have to introduce this before we can do a lot of the rest of the stuff. Your book introduces this at the end, and then it doesn't do a lot of problems with it. We're going to flip this around and talk about this number. So I mentioned before that when I write the log of x, what I actually mean is the log base 10 of x. And it makes sense for you guys to think in a base 10 world because using a logarithm to reduce operations down to exponents, that's about measurements. Things that are really, 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 really far, large distances, planetary, cosmic scale would be very useful to talk about logarithms. Time on a cosmic scale is another one that you want to talk about logarithms more than you want to talk about things. You guys, one of the bigger concepts in any sort of science structure has to do with slow processes happening over very long periods of time leading to discernible change. That's one of the major, major, major themes of science. I can think of three right now: climate change, evolution, and slow processes happening over long periods of time. And that last one, that very, very last one, is the whole thing behind plate tectonics. So a huge 8th grade thing is when you talk about plate tectonics and seafloor spreading. But we have a lot of that happening. And to understand time on a cosmic scale, you have to understand that it's not that there was once Pangaea, the giant continent that had everything. It's that there have been many Pangeas. That has happened several times. There wasn't one ice age. There were lots. Because 4 billion years is a very long time. And things that we can actually detect or observe are only contained within a small bit of that. So while it is possible that lots of things happen that we are unaware of, it's just one of those, to understand the length of time of 4 billion, you have to have an understanding of what the logarithm of that is. There's another logarithm, the LB of x, that we don't really abbreviate LB, but we do use the log base 2 a lot. The final one, though, that we're focusing on today is not LB and it's not LOG, it's LN, which is Latin for log natural. Just basically reverse these two words and you have log natural. It's ln. It's not n as in a variable. It's an operation. I could probably put parentheses around that and say it's the ln of x. When you type it in your calculator, you'll see ln of something. That is a log base e of x. So we need to hone in a little bit, enough that you can work with it, but not so much that you get distracted on what is e. Well, put simply, e is that number. So the next natural question, no, careful, double that would be like 5.4 or something. There is a relationship between it and pi, but it is not a multiple of pi. It's not in the sense of what you're thinking. It's actually far more ubiquitous than pi. Ubiquitous is a word that means omnipresent, and it's very much in lots of branches of math. So pi you see a lot occur in circles. Anything with circles or curvature, you see pi. Pi is the ratio of the circumference to the diameter of any circle. It can be measured by taking the circumference of a circle divided by its diameter, and you will get pi. I mean, we know that. E, you can't find that much. But we can do a little thought experiment that will help you get E. A thought experiment is where you think about something. So let's go with this. Let's say that you have $1 million. We'll just call it a 1. And I'm going to put that into a bank. And that bank is going to be at a certain interest rate. Let's just make it simple. Let's call it 10%. What does that mean for a bank to be at 10% interest? After a certain period, they give you 10%. What's that period usually? A year. So no bank would do it like that, because what would happen is that at 11:59 and 59 seconds on New Year's Eve, you would have basically the entire population mortgage their houses and put all of their cash inflow into the bank so that when the tick over happens, they get the 10% interest and then they withdraw it all again. Okay, they can't work that way. And in times where you had paper for bank statements, that was a nightmare. They actually had restrictions, and then you'd have to keep your money in for so long for it to actually do that. But what if instead of doing 10% once per year, you did 5% twice per year? Now, we run into a small issue, but this is not something you can't overcome. If you do 5% twice a year, then aren't you making interest off the interest the second time? Okay, let's just get over that one, and let's say that interest off the interest is something that's going to happen. But let's say that instead of doing that, let's say we do once a month. So we take the 10%, we divide it by 12, and I'm going to say we're going to make this 1/12, and I'm going to do that 12 times. Now, this isn't a 10% interest rate, but this is basically the same idea. I'm adding a 12, and I'm doing it 12 times. Now, let's say instead of that, I do 1/365 365 times. This means that I'm increasing my value 1/365 every 365 times. What would that represent? You're doing it every day. You're doing an interest adjustment every day. Now, let's say that we do it every minute. How many minutes are there in a year?
A lot. 525,600.
Thank you.
How do you know that?
It's a song.
Yes, my people tend to know that song for some reason, but in any case, that's the thing. Now, let's say that we do it that's every minute. Let's do it every second. Let's do it every nanosecond, every microsecond. We're going to add 1/n, n times. And what happens is that as n approaches infinity, n gets very, very, very large, this thing is equal to about 2.71. This is equal to e. This is the base of the natural log. This is natural growth. This is the growth that we talked about a couple of weeks ago, I think, where I have a bacterium, and then bacteria divide once every hour, but instead of 2 at the end, that second bacterium starts dividing, and then it starts dividing, and that one starts dividing because they actually possess more DNA, and they can actually start to divide themselves. And after an hour, you don't have 2. You have about 2.71 something. So we see it naturally occurring in organisms that can divide. We see it occurring in finance, and we see it occurring in so many other places. In calculus, what you're going to learn is that when I graph y equals e to the x, which looks a lot like y equals 2 to the x because e is not that far away from 2. It looks like this. That's y equals e to the x. A lot of times in calculus, we do things that are looking at the slope of the tangent line at every single point, which is an instantaneous rate of change. This is the only curve on the planet where the slope of the tangent line at this point is the same as the y value. What you're going to do in second semester calculus is you look at the area between a curve and the x-axis. And what you're going to decide is that the area between the curve and the x-axis is actually the same as the value as well. Only curve on that happens. There's a meme that I have that is kind of a fun one. Meme. No, I said meme. Hang on. And this meme is one that, give me a second while I pull this up. You can probably skip ahead 10 seconds watching this on, okay.
Did you pause it?
No, I didn't.
Ben needs to see the meme too.
Yeah, he will.
And burrito.
And
Burrito.
Um,
Burrito.
The cat.
there we go.
Sounds like this, right?
This is one. It's an old one.
Ha.
It's basically saying the derivative of x at a given point of e to the x is the same as e to the x. And while you might not know what a derivative is, and it's fine that you don't, it's exactly the only function that does this. It's its own derivative and its own integral. So there's huge, 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 huge value in e. And for you guys, hang on, knowing how to work with e, knowing kind of the nuances of how to work with it, become a huge factor in this. Yes, Aiden?
You know that weird spirally thingy? Does that have something to do with
It does in a little way. You're talking about the Fibonacci sequence, and we'll kind of deal with that with sequences. You're talking about this, and then 1, 2, 2, 3, 4, and then you start going like that, and that's the weird spirally thing. That's a little bit later. You're thinking more of,
No, I would understand.
it's another irrational number called the golden ratio. But, okay, back to this, guys. So we're kind of settling on this log base e of x, or natural log of x. And it's because you're going to need to work with e exclusively. In fact, in higher math, when you write log without putting a base, you don't mean base 10, you actually mean base e, because there is no base other than e in higher math. But for our purposes, no base means base 10. I'm going to start with some examples like you're going to see on your homework, and I want to model your homework pretty closely. So numbers 1 through 16 of your homework are going to ask you to rewrite in exponential form. They want you to rewrite it in exponential form. So in exponential form, we're going to start very simply with the natural log of 7 is equal to 1.95. Now, I want you to realize that that 1.95 is a rounded value. There's no way that that is an exact value because e is an irrational number. E is not only an irrational number, like pi, it's a number that cannot be the solution to a polynomial with rational coefficients. I say that, it's another way of saying it's not a perfect square root of anything. It's something else. So given that, the ln of 7 is equal to 1.95. That means that e to the 1.95 equals 7. And that's what the question is just asking you here, is to rewrite this in exponential form. To take this, which is in log form, and to rewrite it like this, which is in exponential form. So to do that, we sometimes need to have a little bit of an intermediary, a step in between these two. And if you want to, this is the step that you would write. You would write the log base e of 7 equals 1.95. That's usually going to be the trick that I'm going to say puts all the players on the board. It puts all the numbers that you're going to use on the board to see them. Yes, Eli?
Do we have to do that, or is that just like optional?
You don't have to show that step. But when some of you come in and ask for help about what do you do, I'm going to ask you first to write that step. Because you need to have your brain triggered to see that. I mean trigger in a positive way, not in your submillennial emotional way. No, you're submillennials. You're below millennials. Okay, simplify this, guys. The natural log of e to the 9/5. What does this simplify into? Let me give you a problem off to the side that's about the same kind of problem. The log base 10 of 10 to the 9/5.
Oh, 9/5.
9/5.
Oh, wow.
And if you rewrite this left side, this is the log base e of e to the 9/5. And I asked each of you a question about what that means. It's the exponent that you make e to become e to the 9/5. And that exponent would be 9/5. Therefore, you need to start seeing, e to the x and ln of x as inverse functions of each other. They're inverses. They're opposites. So now it's time to actually talk about these two problems that I said I wasn't going to talk about. I kind of lied. I'm actually going to pull up two problems from last night's homework in context here. And then we'll swing back to E land for a minute. This is one, therefore. 3 dots means therefore. Therefore. You've never ever seen that notation?
Did you just like come up with it?
No, I was taught it in school too.
Looks like a triangle.
Okay, this right here is actually number 38 on last night's homework. And I want to talk about this not from the perspective of 5 raised to the 0. I want to talk about it how I like to think about it. I want to talk about it in the terms of opposites. Because how many of you actually do think in terms of, hey, it's 10x plus 1 equals 5, so let's subtract 1 from both sides. Then let's divide by 10. That's truly how we've taught you to solve equations. So what I need to do is, what's being done to x is it's being log base 3 and log base 5. We need to undo that. Yes? We can, but I'm going to back up. I'm going to worry about this. The opposite of log base 5 of a number is to exponentiate base 5. That's a word that I need you guys to start to inherently understand what exponentiate means. And I'm going to write down a little definition of this transitive verb. Exponentiate, verb, transitive. Transitive verbs are the kind of verbs that have direct objects. Okay. Transitive verb, exponentiate, means to make an exponent of. So if I exponentiate base 5, I'm making it the exponent of a base 5. So sidebar aside, I'm going to take both the left side and the right side of this, and I'm going to exponentiate base 5. 5 raised to the log base 5 of log base 3 of x equals 5 raised to the 0. You guys have been used to moving in the reverse direction where you have the same base on both sides, so you get to drop the bases. We're now going to introduce both bases. Why am I doing that on the left side? Since these are the common base of each other, guess what they do to each other? Pew, pew. They knock each other out. And you get log base 3 of x equals, what's the left side, or right side? 1. Now, let's do the same thing. Instead of exponentiating base 5, we're going to exponentiate with a base 3. So 3 to the log base 3 of x equals 3 to the first. I should have written it like this, 3 to the first. What's 3 to the log base 3 of x? And 3 to the first. And we just took care of that using opposite operations. Big break line, we're now going to return to natural log land.
Whoa, is that for real land?
Sure. So coming back up here, let's say that I have this, e to the natural log of 9/5. What's that? That is 9/5. And we're going to use this sort of as a way to kind of treat and see this as opposites. That's the same as e to the log base e of 9/5. And that's exponentiating base e, something that was being log base e'd. They're opposites. Okay. Another little break bar. We're going to put some rules down. What's the ln of e, the ln of 1, and the ln of 0? These are basic ones that we should know. And if it struggles a little bit, let's write log base e, log base e of 1, and log base e of 0. And what are each of these going to be simplified to? What's the ln of e?
1.
That is 1. And I'm going to put a little because e to the 1 is equal to e. What's the ln of 1? Because e to the 0 is 1. What's the last one? What? Yeah. We'll put undefined or not possible because e to the nothing, we'll put e to the nothing equals 0. It's impossible to take a positive base, raise it to a power, and get 0. So those were the same rules as before. This hasn't changed. Just because it's 2.71, not 2, it doesn't mean it's that different. Break line again. Let's go with number 4. Natural log of 1 over the 4th root of e. I'm going to pause it for a second. Resume. Much like before, if you're struggling with what to do, you can start by rewriting it as a log base e. That should clue you in that you need to write the argument of the log as a power of e. 1 over the 4th root of e is 1 over e to the 1/4, because it's a 4th root. And then the log base e of e to the negative 1/4. And now we're down to what the log base e of e to the negative 1/4 actually is. Negative 1/4. Okay? No. E does not equal negative 1/4. E is a number. It's a constant. That's like saying pi is equal to 4.
Correct.
No, it's a simplification. All right. Now, I want you guys, I really in time want you to get away from writing this thing. The log base e on the left. You should not have to over time. For right now, it's okay, but eventually we just don't want to even worry about the log base e. You guys should see it as it is, much like you don't write the little 2 inside the square root. Okay. Number 5. E to the natural log of 89. That should be quick.
Oh, I got it right. No one cares.
But what if I do e raised to the, let's do e raised to the 2 ln of y. It is y squared. Very good. Because this is e to the ln of y squared, which is just y squared. Let me give you one more of these. Nope, we got many more left, but let's do e to the ln of x plus 1 all over 2. Or what's all over 2 means multiplied by what? 1/2. So 1/2 ln of x plus 1. So e to the ln of the square root of x plus 1. Or, yeah, I'm going to slide this to the left so I can have some room on the right here. What about the log of 1,000? That is 3, just to give you a little review. What about the natural log of 10? Yeah, if you're confused about that one, I would be too. This is asking the question, e raised to what number is equal to 10? There is no good number that would work for that. So this is actually simplified. There's nothing you can really simplify with that because we can't express 10 as a power of e. The best that you can do, and it's really interchangeable, you could also break this up into the ln of 2 plus the ln of 5. And the only reason you might want to do that at some point is if you were given a table of values and you knew what the ln of 2 was and you knew what the ln of 5 was. But I would consider both of these to be about the same simplification. In any case, there's no quick or simple thing that you can do to make that easier. Okay, now we're going to do a little bit of another break line, and I'm going to put that these are now similar to numbers 17 through 22 on your homework, which asks you to combine into a single log. So if we're doing that, and I'm combining them into a single logarithmic expression, this is sort of similar to stuff we've done before. 3 ln of 5 minus 2 ln of 3. Oh, that would be 10 then. Okay. Pretend that ln is just any good old log and use the same rules we did before. What happens to the 3? 5 to the third minus ln of 3. So this gives me the natural log of 125 minus the natural log of 9, or the natural log of 125 over 9, which is bringing it into a single logarithmic expression. That's it. It's a single logarithmic expression. Let's do another one. 5 natural log of 2 minus 4 plus 2x. So the challenge here is that you have a 4. It's not 4 ln, it's just 4, and you have a 2x. But can we still bring it as a single logarithmic expression? Let's start with the ln of 2 to the 5th. Close. We still have a 4. I'm going to give you one strategy. Ln of e to the 4th. Good. Ln of e to the 4th is the number 4. But let me give you a little bit of a strategy for those that like this method here. If we start by knowing that 1 is equal to ln of e, then if I have 4, let's make it 4 times the ln of e, because ln of e is 1. And then I could bring the 4 up as an exponent of the e, and that's a way to get to that. But the key there is knowing that 4 and natural log of e to the 4th are the same thing. Are we clear that you can't combine logs unless they are all the same kind?
Yes.
You can't do anything with them unless they're all the same kind. You can't, what? Same base. And 4 is not a log. What about 2x? Perfect. ln of e to the 2x. And now we can combine them using our rules. 2 to the 5th. We're adding ln of e to the 2x. So this is going to be times e to the 2x. And we're subtracting ln of e to the 4th. Divide by e to the 4th. Now, if you were struggling with the fact that these two were the same thing, let's kind of make this, let's take the number 4, and let's talk about 4 in terms of some other logs that it could be. Let's say I wanted to make it a log base 2. What would I write? Log base 2 of 16. Let's just make it 2 to the 4th, so we don't have to think about it. Or log base 10 of 10 to the 4th. These are all equal to each other. Log base e of e to the 4th is another one. That's the one we just did, because this is the same as the ln of e to the 4th. A lot of times you're going to be taking singleton numbers and converting them into logs of different bases so that you can combine them with other expressions. This is just the version of doing that with ease. Okay, break line. This is going to look like number 23 to 28, which asks you to solve. So a couple of times, some of you guys on the last test actually solved for variables when there was no equal sign. I got into somewhat of a debate with that with another student earlier on a test. And if I have something like 2 to the x minus 1 times 2 to the 2x plus 4, I had several students say that means x plus 1 equals 2x plus 4. That would be true if this was an equal sign, but it's not, and you need to be careful that you know what you're doing. With solves, we're trying to isolate the variable. So in this case, sorry, it should be number 12. I'm going to get the natural log of 1 over x is equal to 5. Now, I want to show you two ways to think about this. There are two equally valid ways. Here's method number 1. In your noggins, you're going to actually think about this as being the log base e of 1 over x is equal to 5. I like to think about this as having all the players on the board. All the numbers are there. You need to shuffle them around into a different order. What order would that be? A to the 5th is equal to 1 over x. That is converting it into exponential form. And that just means that x is equal to 1 over e to the 5th. You might get an answer key that says e to the negative 5, but without directions telling you what form it wants, this is fine. So that's 1 over e to the 5th. Let's do one that's kind of the reverse of this. E to the negative x plus 5 is equal to 4. This is a problem that's an exponent of e. It's in exponential form, so what's the strategy if it's in exponential form? If we're going from log form to exponential form, in this one we're going to go from exponential form to log form, which means a log base e of 4 is negative x plus 5. And I told you I really hate writing log base e, so we're going to write ln of 4. Or ln of 4 minus 5 is equal to x. Or negative x, sorry. Or x is equal to 5 minus ln of 4. Now, a funny-ish multiple choice way to go about a problem like this is to say which of the following is not a solution. Because if I were to write this below that, are those the same thing? Yeah, 4 is 2 squared. And that exponent of 2 can come out. What about this one?
That would be super funny. I would start counting.
So do you keep the ln and 4 like together?
You do, because it's the natural log of 4. Okay, guys, these are all the same. And you have to convince yourself to know why they are all the same. Especially that last one is based off this first one. 5 is the same as the natural log of e to the 5th. Now, Jordan, you asked a good question. I want to hone in on this one for a bit. It's weird for you guys to kind of think of this as a single number. But when I write something like that, that's one number. It's a unit. If I take that and I multiply it by 2, I have 2 times that. If I take it and I subtract 1, this is not the same as the ln of 6. That's a violation of what?
Puppies, yeah.
And not even puppies. Puppies is distributing exponents across addition and subtraction. I'm going more simplistic. I would put this down, which means
Ew.
order of ops. No, oof would be OOF. But this is just saying the natural log of 7 would happen first. Hey, where are logs in the order of operations, by the way? They're not in them. Because the order of operations is trash, like the way you guys learned it. Remember, it's just functions. It's just when do these functions happen? Is this the ln of 7 or is it the ln of 7 minus 1? If I intend it to be the ln of 7 minus 1, I should write it like that. That is the ln of 6. Order of operations completely deals with where groups are. Yes, Janine?
For like number 12 and 13, if you solve number 12 and exponential form, why can't you just keep your exponent?
Because the x isn't by itself. The goal of solving is to get where? Well, 13 was a different problem. In number 12, the x was part of the argument of the log, so I had to do something to get it out of there. In number 13, the x is part of the exponent, so I have to do something different to get it out of there. But in each case, you're trying to get the x by itself. Okay, last example, I'm going to do number 12b. We're going to do 12 in a different way. Nope. I'm doing number 12 in a different way. Right below it.
Well, but I've already gone below.
Well, that's bad for you. Okay. So the ln of 1 over x equals 5. I'm now going to do this with a method that's more opposite operations. This is how I think about it. And this is honestly where I'd like you guys moving towards. I would like you moving away from converting between exponential form and log form. I'd like you moving towards this style. It's going to take some time to get used to this. You have to think about what's being done to x, actually what's being done to 1 over x, and you have to do the opposite to both sides. On the left side, you're taking the log base e. The opposite of taking the log is, what's the word? Exponentiate with a base e. E to the ln of 1 over x equals e to the 5th. The advantage of this method is that on the left side, what is e to the ln of 1 over x? 1 over x. And this is also x is equal to 1 over e to the 5th. The reason I did 12b is because right after that we're going to do 13b. I'm going to do this with opposite operations too. E to the negative x plus 5 equals 4. And I'm going to do the opposite of what's being done on the left side to the both sides as well. What is the opposite of exponentiate base e? Log base e, which we call a natural log. I'm going to take the natural log of e to the negative x plus 5 equals the natural log of 4. Whatever you do to the left, you must do to the right. So on the left, ln of e to the negative x plus 5, negative x plus 5. We said we treat the natural log of 4 as a single number, so just move the 5 over. And when you multiply by a negative 1, it flips the signs around. I prefer it like this, 5 minus ln of 4. It's just prettier. And you get the same thing you got right up above. 2 different ways to do the same thing. Last 2 problems. Oh, I know. It's a big assignment. 14a. We're going to do them right next to each other. 14a. No.
Is there going to be 15b?
Nope.
And 14c.
Okay. All right. I want you to look at these 2 problems. The ln of x squared is equal to 25, and 2 ln of x is equal to 25. They are similar. They're very, very, very similar, but there is one distinct difference between them. I have been telling you that the ln of x squared and 2 ln of x are the same thing. What I have been telling you may not have been the whole truth. And hold with me on this one. Let's solve this with opposite operations. I'm going to do e to the on both sides, exponentiate both sides with the base e. Actually, in time, when I say exponentiate and I don't say a base, the proposed base was always e, because e stands for exponentiate. That's why it's e.
Whoa.
I know. X squared is equal to e to the 25th. What am I going to do now? It's definitely plus or minus, right? Because, you know, e to square, x squared, we still have a plus or minus. Please do not tell me the square root of e to the 25th is e to the 5th. Please do not tell me that. Do not. You're better than this. You know this. Be careful. I know the square root of 25 is 5, but we're not square rooting the exponent. We're square rooting the base. That's different. It'd be 25 halves. Because if I raise both sides to the 1/2 power, I get e to the 25 halves. That halves thing is putting a square root across the base. Okay. What's the difference here that's not going to happen on the right side? Yes. The plus or minus won't happen. On the right side, I'm going to get e to the ln of x equals e to the 25 halves. There's your halves. And I get x is equal to e to the 25 halves. I have no plus or minus. So there is something on the left side that lets you have a plus or minus that is not present on the right side. And that's what I want to close with today. If the negative version on the right side, that wouldn't work because you can't take the log of a negative number, right? But if I have the ln of x squared, what's happening, Jack?
So if you graph those two, on the left one you get like the algorithm, on the right you just get.
And you're one of the few people that's actually pointed out to let's look at a graph, because whenever you want to figure out what is going on, you look at a graph of this. I'll cheat and give you the graph of the 2 of them. Graph of y equals ln of x squared looks something like this. and the graph of y equals ln of, or 2 ln of x looks something like that. They're the same exact graph, except the top one you can graph negative numbers and the bottom one you can't. So when I said that these two were the same, they're the same for all values of x that are in the domain of both. And the only values of x that are not in the domain of the second one are all the negatives. So not exactly the same. But don't worry, that's coming.
You lied to us.
Okay, worksheet, and let's pause.